All right. Hello, everybody, and welcome to today's seminar in the Smart Mobility Connection series. My name is Maggie Harger, and I'm one of the Traffic 21 Women in Transportation Fellows. So happy to have you guys here today. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute, as well as the Mobility 21 University Transportation Center, and it's an opportunity for faculty to showcase their current transportation projects. It's also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. You should note that this session is being recorded and everybody's microphones are being muted. So if you don't wish to be recorded, just keep your camera off. If you have any questions for the presenters, please send a message into the chat box. You don't have to wait until the end of the presentation to send your questions. We'll make sure they're all asked at the end. And now I would like to introduce today's speakers. So first is Keith Redmill, and he received his Bachelor's of Science in Electrical Engineering, as well as the Bachelor of Arts in Mathematics from Duke University in 1989. And then his Master's of Science and PhD degrees from Ohio State University in 1991 and 1998, respectively. Since 1999, he has been with the Department of Electrical and Computer Engineering at Ohio State, initially as a research scientist, and now he is currently a research associate professor. He has significant experience and expertise in intelligent transportation systems, intelligent vehicle control, and safety systems for on and off-road vehicles, sensors, and sensor fusion, GNSS, wireless vehicle-to-vehicle communication, multi-agent systems, including autonomous ground and aerial vehicles and robots, systems and control theory, virtual environment and dynamical systems modeling, and simulator development, traffic monitoring and data collection, deep learning, and real-time embedded and electromechanical systems. So he knows a lot, I think. And then we also have Ekim Yurtsever. He received his Bachelor of Science and Master's of Science degrees from Istanbul Technical University in 2012 and 2014, respectively. And then he also got his PhD in Information Science in 2019 from Nagoya University in Japan. Since 2019, he has been with the Department of Electrical and Computer Engineering at Ohio State as a research associate. His research focuses on artificial intelligence, machine learning, computer vision, reinforcement learning, intelligent transportation systems, and automated driving systems. Currently, he's working on bridging the gap between the advances in the machine learning field and the intelligent vehicle domain. So without further ado, please help me welcome Keith Redmill and Ekim Yurtsever as they tell us about their University Transportation Center project, which is called An End to Driving Automation with Deep Reinforcement Learning Challenges and Promises.
Thank you, Maggie, for that very nice introduction, and thank both you and Joy for inviting us and arranging for us to participate in your seminar series today. With that introduction, I don't think I have anything else to add, so I am going to turn the presentation over to Ekim, and we look forward to answering any questions you might have at the end of the session. Thanks.
Thanks a lot, Maggie, and thanks a lot, Professor Redmill, for the kind introduction. Today, I'm going to talk about end-to-end driving. And when we say end-to-end driving, we mean driving automation, by using reinforcement learning and, the current challenges and promises. Also, this is from Center for Automotive Research, the Ohio State University, and the CITR lab with Professor Osgener. So before we begin and talking about what end-to-end driving is, I want to have like a 2-minute introduction to autonomy, self-driving, and driving automation. I'm going to briefly mention about the official definition defined by SAE, and I will focus on level 3, level 4, and level 5. So in a very brief manner, when we say level 3, we mean limited self-driving. If you have a level 3 car, it means the driver is responsible for any kind of emergency, okay? The automated driving system can conduct certain dynamic driving tasks, but it is not responsible for stopping itself, for avoiding an emergency. In other words, the driver must be always vigilant and be ready to take over. That's level 3, okay? And when we say level 4, we mean full self-driving, however, limited by certain conditions. So if those conditions are met, and I'm going to talk a little bit more about those conditions, but if those conditions are met, for example, if you're in a very limited area with predefined, baked in a priori information, such as, a certain district in San Francisco, then the system is responsible for emergencies also. However, it is limited by that condition. And that condition is most commonly is a georeference or a geofenced area. But sometimes some people take level 4 as a limit to operational domains also. If you say only highways, that is a limited operational domain, but you can also, say any domain inside this geofenced area. And level 5, and nobody is never near level 5, is full self-driving. If a human can drive on a piece of road, a patch of road, anywhere, let's say in the US, then we expect the vehicle to do the same, but nobody is even close to achieving level 5. Okay, and some companies claim they have achieved level 4. We have certain demonstrations, but we don't have a widespread deployment. Okay, so let's take a look at the most common automated driving systems framework and system architecture. Okay, so the most common, let me activate my pointer. Okay. The most common and conventional approach is using a modular stack of algorithms to map the sensor space to the action space. When we say sensor space, it's like humans. Our eyes are our visual perceptors, right? So we perceive the environment through our sensors, and then we go through a process and execute actions. In driving, those actions can be limited to steering wheel angle and acceleration, pedal position. So the goal is going from your sensors. It might be only RGB cameras. It could be a suite of sensors, multiple sensors. It could be fusion. We might have LiDARs, radars, and cameras. The goal is going from here to the action. Now, one idea is decomposing this huge daunting task into easier to solve sub modules. That's what we call a generic modular system pipeline. Now, the idea is we will have separate pieces of logic that does a single task or a cluster of tasks, such as only detecting the objects, only localizing the vehicle, only assessing the scene, or only predicting other vehicles' behaviors. Okay. Now, this has certain benefits. Why? Because it makes, when we decompose the problem to easier to solve smaller problems, it might help us to solve those problems faster. But we sacrificed generality, and we become very brittle, and we lose robustness because imagine, this, I don't like biological references, but this is a good metaphor. Like, as humans, when we drive, do we have separate pieces of logic that is completely independent going on in our brains? We do object detection separately, we do tracking separately, we assess the scene separately, we make our plans separately, and we don't share the inner workings of these logics between each box. No, in other words, this is not, when you approach the problem and you build your system modularly, it is easier to solve, yes, but you don't have a general consistent policy or decision-making process. And for example, your object detection or your uncertainty in the object detection maybe should be used in the planning and stuff like that. So Because of these reasons, in the very recent years, people try to come up with one algorithm or one policy that can map the sensor space to the action space directly. And with the recent developments in the deep learning and reinforcement field, we are now able to come up with general policies that can actually map the sensor space to the action space. However, it has also certain other shortcomings. That's why today I'm also going to talk about hybrid approaches and what we did at OSU to combine these approaches to have the best of both worlds. So before I begin and talk about end-to-end driving in detail, I will briefly go over the individual tasks to give a general idea of what's going on here. So in a modular stack, when we have a camera, we need to we have these separate perception tasks. For example, A is what we call object detection. We want to detect every single object in the camera frame. And then we might also want to do semantic segmentation, which is shown with C. When we say semantic segmentation, what we mean is classifying every single pixel in this image with respect to its semantic category, okay? And furthermore, what we can do is if we have LiDAR, we can get distance to those objects. Now, why do we have multiple sensors? This is a good example. Look, when we have cameras and RGB image, we have texture information and we have very dense information. So it's actually very easy, even as humans, to detect every single car, the type of the car, their textures in the RGB domain. Look at the LiDAR domain. In the LiDAR domain, it's so difficult to discern the details of objects because we don't have that nice color and texture information. However, in the LiDAR domain, we have distance information, okay? So because we shoot a laser beam and measure its flight time, we have distance. And on the other hand, on the monocular camera, we don't have depth. So we can compensate the weakness of both sensors by using both of them. So that's one general idea. So, okay, so that's for perception. After perception, if you have a modular stack, you need to do something like estimating the danger of the scene or understanding whether you're in an emergency or not. And I'm going to go over one approach to give a basic idea. So this is what we did in 2019 between a collaboration between Japan and OSU. So the idea is, can we holistically represent the risk level of a scene with a single function? Okay, so if it's safe, tell us it is safe. It is dangerous, tell us it's dangerous, and also quantify the dangerousness and the safeness of the scene, with a number. And then our job is done because this is modular, right? After we get that number, we give that number to the planning. So the most common approach for these kind of vision tasks is using supervised deep learning. I will not go into much details, but I will just go over the architecture and the training loop once, and then I will move forward. So the way we come up with deep learning solutions for these kind of driving tasks is, first, the machine learning engineer comes up with an empty template. Okay, the empty template is, we look at the problem and try to understand what is the compositional relationship of the data. In this case, we have a spatiotemporal problem. We have space, what's going on in one video frame, like things related in space, and we also have a temporal relationship. So our architecture should be able to capture both space and temporal relationships. Now, because of this, in this study, we proposed a CNN-based feature extractor plus a Mascar CNN, and then after this architecture extracts spatial information, we concatenate and we fuse this spatial information in a temporal neural network to understand the spatiotemporal encoding of the scene, and finally we add a classification network. Now, this is a template. We as engineers, we think that this should be able to capture the problem. It's like an empty brain, if you will. Now, after this, if your template is good, then the next step is training this template. And in order to train this template, what you need is a structured annotated and labeled data, right? So if we have thousands of video clips, and also if we have labels such as safe or risky, or a score of riskiness and a score of safeness, if we have that paired data set, then we can use that data set to update the weights of this empty template so it will learn to solve the problem. That's the general idea of using deep learning for a single task, okay? And this is called supervised learning. However, we are limited by the requirement of such a data set. And here, I will not talk about supervised learning anymore. I will show a couple of other modules in the modular stack. So here you see a open source software. This is Otoware. I was part of the group who developed Otoware in Japan, and I will not go into much detail, so please check their website for details. But the idea is they have all of these individual modules, and in order for the vehicle to drive, you need to first find yourself. That's called localization, and then you need to detect other vehicles, and then you need to make a plan, and then you need to follow that plan with a controller. Okay, that's the main idea. Now I will go over a couple of strategic modules. Arguably the most important module in the modular stack is localization. Okay, so the idea is, can I find myself in an a priori predefined representation of the world? Okay, and you will say, oh, just use GPS, just use IMU, just use dead reckoning. So those methods works fine, but we cannot get centimeter or millimeter level accuracy. So one of the most common approaches for localization is using something we call point cloud matching. So the general idea is the colored point clouds that you see in this video are the online scans. And the objective is trying to find those the best match between the colored points and the ocean of white points. So the white points are collected before, okay? It is an offline 3D point cloud map. And the green points are online scans. So if you can match your online scan with the already existing white point cloud, then what you can do is you can localize yourself in a predefined world. Why do we want this? Because if you can do that, then you can bake in or simply manually put all the necessary information about the world, such as the position of the lanes, such as the speed limit, such as the where the traffic lights are, the traffic rules, and you can boil down the problem. You can decompose this problem into a simply line following robot, if you can do this, of course. But this process is extremely expensive, right? Like first we need to find ourselves in a predefined point cloud map. And then moreover, like we need to define the semantics of the world, by human annotators for a very limited area. If we can achieve that, then yeah, go ahead. You can drive level 4. But that's why the current level 4 is limited to only, for example, let's say one part of the world, right? Because this is so labor intensive and this is so difficult to do. It is not scalable. And moreover, it is also brittle and prone to fail when the world changes, right? Because we update the world once and then we assume the world will not change that much. But that's not the case, right? We always have these small temporal changes in our world because of a construction, because of the weather, the point cloud can change. These trees, can be cut down, for example, and then your matching algorithm will fail, okay? So because of this reason, can't we replace all these modules with a single general policy and just learn to map the input space to the output space? Okay, so that's our main objective, and that's the main motivation behind using end-to-end neural networks. So there are a huge body of research, and I cannot do justice. Just please check Kendall's, Chen's, or Banzel's work. But in summary, we have the modular approach. It's easier to solve, but it's complex. It is prone to error propagation, and most importantly, lack of generalization outside pre-postulated model dynamics makes the system brittle. End-to-end, on the other hand, promises a general solution. However, we don't have hard-coded safety measures, or we don't have interpretability. And also, it's actually very difficult to do generalization. Now, one question would be, and we think it's an understudied subfield, is can we have the best of both worlds, like a mid-to-mid approach? So before I introduce our solution, let me go over a very high-level summary of deep reinforcement learning. So when we say deep learning and when we say machine learning in general, the most common categories that people use is the taxonomy is you have unsupervised learning, semi-supervised learning, maybe self-supervised learning, and then supervised learning, and then separately you have reinforcement learning. The biggest advantage of deep reinforcement learning is we don't need labeled ground truth data. We absolutely do not need data in reinforcement learning. Data is created through interaction of the agent with the environment. So basically, the agent that we try to train collects its own data, okay? However, that brings us the con that is actually a disadvantage, because if you need interaction, that means you need to be tolerant for failure. It's like raising a child, like raising children. If you want the child to learn, you need to let the child to try to try to execute actions. And if he or she fails, you don't, throw that algorithm and say it's bad, right? You just tolerate it, and it continues to learn. However, in driving, we cannot just go into the real world and try to train our deep reinforcement learning agent by interaction, because it needs to fail a lot to learn the correct policy. But obviously, if you fail a lot in the real world, people will die, okay? Because of that reason, we require simulation. That is one disadvantage. So our objective was to combine best of both worlds and try to train the reinforcement learning agent faster. Fast means less interactions, and less interaction is one of the key disadvantages of reinforcement learning, because if we can target that, then maybe we can make this technology feasible. And also, we want to integrate more explainable and flexible modules into this general policy. So the idea is we try to integrate a model-based path planner, actually it's a heuristic-based path planner, into a DRL agent, and then we trained the agent to resolve conflict and learn to follow the path. And our main idea is we have a DRL branch that maps the input space to the action space through the upper branch. This is like a regular end-to-end DRL network. And then we also added a very simple path planner and concatenated the path, the waypoints, with the features learned through a CNN to come up with a good policy. And I am running out of time, and I will not go into much details, but the key mathematical formulation for reinforcement learning is something called a Markovian decision process. And if you can define driving in a Markovian decision process, then you can use algorithms that tries to solve the MDP. Now, MDP is a very strong formulation. It tries to capture the stochastic nature of the world, and it also tries to capture how can we argue the goodness of decision making, okay, faced with uncertainty. So in a Markov decision process, we have a 4 tuple that represents the world with S. This is the state space, what's going on around our world. And then we have our action space. And in our case, the action space could be, if it's discretized, all possible combinations of steering and acceleration. So it is what the agent will do, okay, the action space. And then we have P. P is very important because it models the uncertainty of state transition. Let's say if you have a truck in front of you and you decided to brake, okay, you know what's in front of you and you know what you are doing. However, there's still uncertainty because in the next time frame, something from the sky can fall in front of you, and maybe you can make an accident, stuff like that. So in order to represent the driving, you need to have that uncertainty. So absolutely it must be indeterministic. And then the goal is trying to maximize an expectation that will cumulatively have the largest cumulative rewards with an infinite time horizon. In practice, we use a finite horizon. And that was the theoretical background. So in order to find that optimum policy, which means, the policy that will maximize that expectation, we use something called Q-learning or a DQN agent. And what we do is we concatenate everything through neural network layers. And then our neural network outputs certain Q values. These Q values should represent that expectation, or more or less. It's actually not, it is a value. But then what we do is we pick the maximum value and the corresponding action, and that's how the agent drives. Okay, and I will not go into more details, so please do check our paper, but we need to define a reward function to represent what good driving is. So you only do it once. If you try to learn this also, that's called inverse reinforcement learning, but that is out of the scope of this, of this presentation. So we need to come up with a good reward function that will represent the goodness of driving. After that, then we can train this agent. And what we did is we used a driving simulator to train the agent, to follow waypoints. So at the beginning of the training, as you can see, the agent is very slow and it learns very slowly. And because of this reason, we cannot go into the real world. Okay, but then, and also sometimes interesting things happen. Okay, so we asked the agent to follow the green path, but the agent decided to go home and said, I don't want to be part of your training. I don't want to do this. Okay, so in other words, we cannot go to the real world immediately because of these reasons. Okay, and we should just ask nicely also. But eventually, if you can finish your training, then the agent actually learns to follow any given path in any traffic situation. As we can see, at the beginning of the training, the agent failed a lot, but at the end of the training, the agent successfully learned to drive end-to-end. Okay, but we also try to resolve conflict. So in other words, we put a vehicle on top of our trajectory and we force the agent to follow that waypoint, but we also ask the agent to not make an accident. So we checked whether the agent was able to resolve conflict between the model-based planner and the visio-perceptive features learned through the CNN. And even though we have some promise, this is still, an open problem. So let me introduce a couple of results. So we compared our approach to a vanilla DQN, and we saw significant gains in training time. So at least we can say that we can use our technique to spool up the learning process of any DQN-based end-to-end driving framework. However, we also conducted further experiments and find out that the agent is still not good as a human driver. So it's obviously still an open problem, and we still need to do more. And I'm going to introduce one single slide of another work that we did at CITR. And this work is all about, right now, we are confined into the simulation, right? So we need to take an extra step and we need to map our simulation to the real world. And in order to do that, we trained a state-of-the-art GAN, and we tried to convert our simulation image, the semantic layout of our simulation image, into a real-world looking fake representation. So this is not from the real world, but we use the neural network to go from here to here, so our final image would look like the real world. Okay, why? Because we want to train our network in a more photorealistic driving simulation, or more importantly, not photorealistic, but a representation that will look like the real world. This is different because you are limited to your sensor modality. So sometimes we have these conventional rendering engines and they look very nice, shiny, and pretty, but actually that's not how the world looks from a lens of a camera. So our goal was to go from here to here. So this is still ongoing and we have our preprint available. But our final idea is, if we can finalize this work, then we will repeat our experiment in this new simulated world. And then finally, maybe we'll be able to deploy in the real world. Okay, so it's a long shot. Okay, so the summary, the proposed method learned to drive faster and showed some general conflict resolution ideas. I have a chat message. Okay, and then, however, we also find out that we are still not good as an average human driver. And believe it or not, and it might be counterintuitive, but humans are very smart. When you do this kind of work, you quickly realize how intelligent humans are. Before working on AI, I thought maybe humans are not great, but actually we are. All of us are pretty good. Like, for example, driving is a really challenging task, and the AI is still struggling a lot. And for future work, of course, we will try to integrate the better planning algorithms, and we will focus on spatiotemporal networks. And let me conclude my presentation. I think I have 1 minute left. So as a conclusion, what we can say is vision plays a key role both in the conventional stack and end-to-end driving, right? We can also say localization and a priori matching in the modular stack is a bottleneck. Like, it is one of the biggest bottlenecks that limits the widespread deployment and scalability of ADS. On the other hand, end-to-end algorithms are promises a nice solution, but still struggles to achieve good driving performance. And of course, if you are going to use end-to-end algorithms, then we need to find a good solution to the simulation to the real world knowledge transfer. And simulation to real is also very important for simulating edge cases, because in training these networks, the data that we need the most is dangerous data, like accidents or hitting a pedestrian. But if we go to the real world and collect data, then we will not have that many edge cases. So if we can create those edge cases in the simulation and then make it look like a real world, then hopefully our algorithms will be ready for emergency situations in the real world. So this concludes our presentation. So our code base is completely open sourced. So, please, we can use as you will. And thanks a lot. If you have any questions, please ask Professor Redmill, or you can reach my email. I think I'm done.
Great, thank you. I have a few questions in the chat. The first is, I am interested in the Markovian assumption because that really simplifies the problem. How do you justify that assumption?
Sure, very good question. So before, I have not showed you, but actually, people draw in the real world with a simple MDP in country words. But before that, let me try to activate my. I need to be able to annotate this. Nope. I'm going to spend 5 more seconds trying to activate my pen. And I also want to stop. Okay. Let me share my screen again. Okay, can you see my screen?
Yes, we can.
Okay, so the fourth tuple might look simple, and if look, this is a high-level abstraction of the world, but it actually captures the uncertainty, because in practice we never know what P is, and we don't know what R is. So P represents our world dynamics. But we can put it in a mathematical formulation, right? We can put all the uncertainties into P, and then on a higher level, it will capture the real world. However, it's just we don't know what P is. So in practice, none of the current algorithms obviously can capture what P is, what is the uncertainty of state transition. But the current algorithms, what they're trying to do is they try to make an estimate value approximation, and they try to at least get a nice estimation of this expectation. If I conduct this action, will I be a good place, let's say, in a finite event horizon? I still have uncertainties, and I cannot model the uncertainties because it's super difficult, but maybe through experience, I will store some useful values. Now, if it's not perfect, but if you can learn such a good policy, it's like humans, right? Like imagine driving, and can you guess what's going to happen in the next 25 seconds? Maybe not, right? Because there's too many uncertainties. But maybe if your policy focuses on the next few state transition, and it's represented with this discount factor that puts more importance on the immediate state transitions. For example, what will happen in the next 5 seconds? So the MDP process and the DQN algorithm tries to somehow optimize that limited horizon. And in that limited horizon, it has been shown actually that you can drive, for example, in a country road, with very light traffic. I'm sorry if that was a little bit long, but I tried to explain the MDP. That was a technical question.
Okay, I have another question. Would you explain a bit how you define the state or environment and the reward of your algorithm?
Okay, perfect. The state is, if it's pure end-to-end, it's your image. That's our state, right? It's the environment, it's what's going on in the world, or how we sense that environment. In our case, we expanded our state space with our own speed and distance to the next waypoint, okay? So that's our state space. And our reward is, we used a reward function that is commonly used by other people. Basically, it represents, don't make an accident, try to reach your goal, don't drive jerky, and don't do a lot of, lane change violations, stuff like that. So we use a predefined function with just those 3 or 4, postulated world dynamics. And then, but the trick here is we don't want a very pedantic reward function here for several reasons. But yeah, our reward function looks like that. So this is the velocity goal. This is the no collision reward, driving close to the speed limit. We don't want to go over the speed limit, but we don't also want to drive very slow. And then we also want to get close to the destination. And then we want to follow the planner's waypoint. That's it. Yeah, if you can do this, then the agent learns to drive and solve, complicated, planning issues with randomly initiated episodes.
Okay, do you anticipate that the automated vehicle will ever be as good as the human driver?
That's, I think, I don't want to say, there might be no answer, because, when you say, it's like, are painters good artists as singers? If I ask you that question, would you be able to answer that? So in other words, the automated vehicle will drive in a completely different way, and the humans will drive in a completely different way. Now, we can, of course, try to quantify and come up with this very high level performance metrics. For example, if the answer is our automated driving systems going to make less accidents, or stuff like that, then probably it should happen, right? Otherwise, we will never deploy that. But maybe it will never, even though in aggregate statistics, maybe the automated driving system will make less accidents, but maybe when there's an emergency, they will fail and they will perform worse than a human. For example, if we drive as a human and a deer suddenly jumps in front of us, maybe we might be able to evade that accident by doing something crazy, but also smart. I think ADS will not reach that in the foreseeable future, but ADS will never sleep on the road. ADS will never violate the traffic rules. ADS will never try to drift on the middle of the street, stuff like that. For the normal operational domain, it can minimize the accident rate in such a great scale that on an aggregate level, it can reduce fatalities. But in my personal belief, for example, for stuff like edge cases or extremely fast generalization, we are not there yet. Humans might be, for a foreseeable future, can be, but I think that's not the goal. The goal is not beating the human in every single possible way, but just, reaching a point of robustness that aggregately it will reduce fatality and it will increase efficiency by allocating driving time. So yeah, I cannot answer that question because I don't know what is, the goodness of driving needs to be defined carefully. I try to explain mine.
Okay, no, that was great. How did you get interested in this research topic?
Right. Very personal question. So, I think, doing a PhD is, I think, during your formative years, if you do a PhD and if you have a good research advisor, and if you read and learn a lot what's going on around the world, then it will, your intellectual curiosity will go into certain directions that, it's all about that, in my opinion. So during my PhD, I started to be, 6 years ago, be interested in, math, statistics, things like hidden Markov models. And then at the same time, we had this big boom in deep learning and automated driving. And then naturally, I shifted, towards that. And I think it's just a learning experience. So yeah, I think, doing a PhD is great because those reasons.
Awesome. Any thoughts on how you can adjust your steering and acceleration output from the network to provably guarantee collision avoidance and safety?
Right. So look, so we need to go back here. So when you have, and let's talk about end-to-end in general and forget about our hybrid approach. If it's completely black box, then right now there's no reliable way to absolutely guarantee the safeness of the black box. Okay, you can develop you can prove theoretically that your empirical excitation method will test it so well that you can depend on the output of that external testing strategy. But I have my doubts about that. Now, if you have hybrid systems, you can try to come on. If you build very nice mathematical assumptions, then you can theoretically show that if those certain criteria is achieved during training, and if my optimization space looks like this, then I can safely say I will be able to follow these kind of waypoints with these kind of error margins, and then you can try to prove the path planner and the waypoints that you get, and then add the uncertainty on top of that waypoints. But this is a very speculative answer. But of course, that question is very essential, right? It's a very, very important question. Can we provably, show these algorithms will be absolutely safe in real world in every possible condition? So in my opinion, of course, doing this theoretically is not possible, because in order to make this work, you need to make certain assumptions, and then you can only prove inside those assumptions. So you need to have this empirical framework to maybe excite things and test things rigorously. But this is much, I don't have a conviction here. This is a very hot topic, and proving things whether they are safe or not. This is one of the most, if not the most important challenge for deploying ADS into the real world.
Okay, where do you see this research going in the next 5 to 10 years?
So if this only, by this, I mean the whole field, I guess, not just our work. So if it is, and if by this, if it includes all automated driving systems, then we have 2 or 3 distinct candidates. So, for example, people at Tesla has a different approach. What they do is they collect data with LiDAR, radar, and very detailed information, and then they train very big, slow neural networks to automatically annotate billions of scenes, and then they use those network and they try to distill that information by smaller networks that just use camera and can be deployed in the real world. And they also have a modular approach, but they rely on vision heavily. And for example, for stuff like they don't use baked in information like this. So they use something like a mid-to-mid approach. So given a sensor's input, they try to create the world, and also they try to build the semantics separately, and then they use planners that are more conventional and rule-based, to construct certain plans. So that, in my opinion, the robustness could be increased to a certain level where it can actually be deployed on a very limited, not very limited, but almost non-limited way. But it will still be limited. So there's one approach. The other approach is, if we talk about end-to-end, in my opinion, it's very nascent. We're at the beginning of end-to-end deep reinforcement learning. We still need to solve a lot of issues about these algorithms. But it's so recent, right? Like the moment that a deep reinforcement learning based algorithm beat the human Go champion, it is so recent. Like it's this decade. From there we are trying to achieve fully autonomous driving. I mean, in my opinion, it will take a very serious amount of work, but there's absolutely a promise, a very strong promise in this direction. And we can always find the middle grounds. And of course, like a tree that has branches, we will have these subfields, in my opinion, that will try to increase the feasibility of like deep learning based methods. Like how can we increase interpretability, explainability? How can we try to measure the safeness of a learned policy? Can we look into the way that the weights are learned and come up, with a mathematical framework, to represent that process, stuff like that. So I think, and of course, how can we utilize more data? Can we use self-supervision? How can we, make our simulations look like the real world, stuff like that. So we need maybe more enablers in this field, but for sure in the next 10 or 15 or 20 years, we will have more progress. So we will get a little bit closer to learning a general policy. So I don't know if we can achieve artificial general intelligence, but maybe a general driving intelligence is in the realm of possibility, for the next 30 years or something like that. That's what I believe.
Okay,
but it's still
great.
difficult. Yeah.
I have no other questions, so thank you very much for the presentation.
Okay. I don't see the audience or I don't see the chat, but are we done? Do we have?
We are finished. Thank you very much.
Okay. I see a hand from Inci Özgünes. Is there? Oh, the hand disappeared. Okay. Okay.
I lost the hand there.
No.
All right. Well, thanks everybody. Thank you, Keith and Ekim, for sharing your work. And to all today's attendees, thank you for joining us at today's seminar. As I mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page of our website, as well as a link to the video portion of the session. And this afternoon, you'll also be receiving an email asking you to take a short survey about today's SMC. So please take a few minutes to provide your feedback about it. For students who are interested in engaging in transportation topics, I want to promote also the Transportation Club as a great way to get involved in the transportation community on campus and interact with fellow transportation nerds. And then also our next SMC will be Friday, November 12th. So that's 2 weeks from now, and it'll feature Pulkit Grover. So watch your email inboxes for an invitation to join us closer to that date. And yeah, thanks again for attending, everybody. Thanks for the great presentation. And please feel free to reach out if you have any additional questions. If not, enjoy the rest of your day.